Good morning. Today we are going to do the form finding for this cable suspension bridge that I think is quite familiar for some of you. So it is a semi-arched solution with a backstay cable and tension cable deck. This is the bridge we are going to solve. I'm going to put in the web page the input file so you can modify it and work based on that. So there we go. The input file is as usual. It has several blocks. The first block is group divider, system parameter, the maximum number of iteration, maximum displacement per iteration, maximum increment of tension per iteration, and maximum tolerance just to stop the calculation. The second group is to export the export parameter, the group divider for export, that is the same for calculation. This one, export quadrant divider, is something I'm going to explain in the future, but should be always one digit less than the export group divider. Then export parameter for the different group 1, 2, 3 and 4, that I'm specifying beam, cable and cable, and it's the deck, the mast, the cable and the stay cable. I'm specifying for group 1, that is the deck, a weight, so I'm assuming a 30 centimeter thick concrete slab. So in the second parameter I'm introducing the weight per length of that member. Then I'm specifying the nodes. Start group 1 is for the deck, group 2 is the mast, and group 3 is the back cable. So this node here is now 3000 or 30,000. Then the elements that are elements for the deck, elements for the mast and cables. And then I'm specifying relative length, so all the elements of the mast has the same length. And then fixing node plane, so I'm forcing the node to move in one plane, so fixing those nodes to not to move in one direction. And this is pretty much the input file. So I'm using just two different type of geometric constraint, the relative length and the fixed node plane. With this we go to the software. I'm loading the input file, plotting the node numbering. 30,001 is this back node, 10,000 are the deck, 20,000 is the mast, 20,010 is the top of the mast. You see that there's a kink here because I don't need to be precise in the construction of the geometry. The mast I'm introducing as a starting geometry as a vertical mast, and then the last node is going to the direction, to the position where I want to have that node, and then during form finding the software is going to move all these nodes to the proper place. Then I'm specifying with this window you can control the geometric constraint. So if I go for one of these, you see this white line here that is specifying the relative length between node 20004, 20005 and 20005, 20006 to have the same length. This one here, and these three numbers is in three components, X, Y and Z to process the same length. So if we go for the next one, it's climbing the mast. So here I have a visual representation of the geometric constraint, and then is fixing plane. So the first one is I'm fixing all the deck nodes to not to move in a vertical direction. So all the force will have to go to the cables in the vertical component, and also I'm fixing the node not to move in X direction. So I'm not allowing this node to move horizontally, but if we go here, I have this restraint that is I'm fixing the node in Y direction because the model is symmetric. So at the end is going to be a beam here between this side of the bridge and the other side of the bridge. So you can simulate that as a fixation that creates a reaction. But this plane fixation is not allowing the node to move, but it's not creating a reaction. So everything is, all the tension in this cable vertically is going to be compensated with the weight of the deck, and horizontally is going to go through compression in this beam. And there we go. If we select all, you can see all the plane restraints I have in the geometry. I'm fixing all these deck nodes vertically and horizontally. This node is fixed horizontally, so all the force is going to go, horizontal component of the force of the straight cable is going to go to the deck. And the top node, I'm not allowing the node to move vertically nor horizontally, so this node is also fixed, but without creating a reaction. So this is the difference between a finite element software and this software. Like with this software you can fix nodes and you don't create reactions. Well, let's say once we have this model, you can see this view, you can see the front view. So I have created the mast vertically, and only the last node is the one that is placed in the symmetric plane of the bridge and at a certain position. This is from the top. So we have a pretty much approximate geometry, so it's quite useful to have a geometry that is more or less approximate to the starting geometry. So if we run the form finding, you can see after 8 iterations it has reached the equilibrium, and there we go. We have the bridge, the semi-arch with the exact geometry. If we check the length of this member, 1.087 should be the same in all these members here. You see, Then the deck is every 2 meters, but is fixed by starting geometry, but the load is incrementing here, the load. So you can see that that is happening. 500, 480, and then the stay cables, the suspension cables, they have more or less same geometry, and the back stay cable. So this solution is a solution that is in perfect equilibrium with all the geometric constraints we have specified. Now we can see it from top, side view, and front view. Now you can see that the mast went exactly to the plane of the suspension cables. And once we have this geometry, we can save it. So explore, save it, and save. And in this file you have now is the output file. FormFinding output is exactly in the same format as FormFinding input, but now you have all the nodes with the equilibrium coordinates, all the members with the equilibrium forces, and all the geometric constraints used, and the others are 0. So it's quite useful to save the result. And now we are going to go to export. The first thing to do is to evaluate the model, because we have specified the block of export. It is automatically picking beam, cable, and cable, and the names for the different groups. Then we have to choose symmetric in XC direction. This is X, this is C, so it's symmetric. So when we go to export this, we are going to create the symmetric model, and then we are going to generate in the memory of the computer the model. We are going to save to DXF, yes, and save the file. The problem is that I have in Autocad the file already open, so I'm closing the file, going again to this and export the file. You see it work, and I haven't tried it before, but I'm going to save it for Sofistik. Yes, it worked. And once I have exported, I can go to export, bridge C. We are going to disable comments, elements node, node numbering, and nodes point. We have the bridge. I'm going to change the style, and there you see that the software has assumed some compression, some cross sections for the cables and the beams, and this beam that are assuming the deck is assuming a pipe. This is why they are so big. So for the deck we are going to disable this group 1 3D, and here we have the bridge. From the top view of the bridge, side view, front view, and side view. This is the solution for this bridge, exported to DXF. Closing, not saving, and we will try to open with Sofistik this file. Aqua should work. No, one error. I haven't seen the error, but Sofistik PRT memory allocate private data change of the structure of this record. Please compare the current. Well, but just taking a look, normally is problem with the cross section of this. I'm going to specify 0, 0, we will see. No, same problem. At position 14. Let me see. Here it is. Stay 60. Well, doesn't want to. We have to spend a little bit more time to check what is going on there. And this is the geometry. For the geometry it worked, but we shouldn't have cross section. Well, we have the geometry. It seems that the issue is not a serious one. So we have the bridge in Sofistik, just to check that error in Aqua module. But we have the cross section, we have the geometry, symmetric geometry with the fixation. We have to remove all this fixation and replace them with beam, but it's a minor work we have to do. And we have a geometry that is in perfect equilibrium. And here we have module Sofiload with all the pre-stress you have to apply for the different members. So this is all for now. I hope you enjoy. See you next time. Bye bye.